Good morning, everybody, and welcome to this plenary session on the last day of this year's annual conference of the EAERE Association. My name is Erik Nevdal. It is an honor and a pleasure for me to introduce this morning's plenary speaker, Anne-Sophie Crépin. I am very confident that the insights she will present today on well-being and risk of abrupt events will be interesting and illuminating. I have known Anne-Sophie for 25 years since we first met at the legendary Leuven Annual Conference of Environmental Economics and Management. That's a tip. At the time, we were both interested in the same thing. We were applying sophisticated mathematical tools to what was at the time unorthodox problems in environmental economics, where the standard tools of conventional economic modeling had to be modified. Anne-Sophie's work on coupled ecological systems, tipping points, and the application of fast/slow process to complicated dynamical system was way before its time. The fact that her dissertation was awarded the prestigious Arnberg Prize by the Royal Swedish Academy of Sciences is a testament to the quality of her early work. Since then, it has become even better. However, Anne-Sophie was not satisfied with solving funny math problems. Under the partial guidance of her mentor, the late, great Carl-Göran Mehler and Carl Folke, she became a pivotal part of an impressive effort to bring economists and natural scientists together at the Beijer Institute of Ecological Economics. Thereby, she facilitated knowledge production on a very impressive scale. I could read you the list of names with outstanding research output that became deeply involved with this effort, but if I did, we'd be here all day. But shout out to Arte Suv over there, who was part of it. So Anne-Sophie's influence on environmental resource economics is only partially reflected in her very impressive list of publications. In her role as facilitator and catalyst for interdisciplinary research, she has accomplished more than most. I ask you all to give a warm welcome to this session's speaker, Anne-Sophie Crépin.
Thank you very much, Erik. Thank you so much for inviting me here. I feel very honored to be here. I've been part of this conference for many, many years, and I didn't know I would end up on this stage at some point. So, can I get the presentation on, please? Thank you. So my presentation is titled Long-Term Well-Being and Risk of Abrupt Change, a Journey. And the reason it's a journey, it's because I will not only go with you through the road I made to do all the type of research I've been doing, but I will also talk about how it has been possible thanks to the help of many people in many different fields, as Erik highlighted. So I want to start with these pictures that came out from the Stockholm Resilience Center, which is my second affiliation after the Beijer Institute. And they had this very nice picture in the today's annual report, or this year's annual report. You can tag this thingy there if you want to see it online. And it's really nicely illustrates the kind of journey. It's not my journey, this is the Stockholm Resilience Center's journey, but a lot of this journey has been parallel with mine, and showing how different type of disciplines have interacted, how I've borrowed from complexity thinking, from collective action theory, from environmental economics, from ecological economics, and from ecology and all kinds of theories that have been put together to create, I hope, a better whole than just by standing alone. I have the pleasure to meet a lot of different research from different fields, which have helped me develop a lot of different types of tools. And these are the type of tools I've been using the most. And it's a very strange mix of optimal control theory, game theory, dynamic games, behavioral experiments. I've made a lot of synthesis and perspective papers thanks to the Ask meetings that we have every year at the Beijer Institute. I've been part of developing resilience thinking. I've used a lot of complex adaptive systems approach, dynamic modeling, and more that didn't fit on this slide. And I've used all these tools to look into broadly this type of question. How can society deal with the risk of abrupt change in a way that sustains long-term well-being? And some of the insights I will talk about today are in a paper that is in press and will be published pretty soon in the International Review of Environmental and Resource Economics, and which that paper has this content. So we look at how to model threshold, how uncertainty comes in there, management challenges associated with tipping points, and where the tipping points are risk from, motive for precaution, and we're also looking into behavioral experiments there with tipping points. In this presentation, I will pick a bit of these pieces and a bit and some other points that I will show you soon. First, I will want to just, for those of you who are not familiar with these concepts, I will present to you what type of abrupt changes are we talking about. So I've been looking most at changes in ecosystems. It could be lakes and seas or coral reefs or forests or fisheries. And this type of change we're looking at are, for example, so the, I have to learn this thingy. So the first pictures here shows pictures of the Baltic Sea, which has, according to ecologists, experienced a regime shift during the 1980s, where it went from a clear sea to now a sea that every year exhibits algae blooms, and you see the algae blooms in greenish things. And that's quite troublesome when these algae blooms come, because that's when we have holidays on the island of Gotland that's on this picture. And when the algae blooms come, you just can't swim anymore. You can't use the sea, which is really what you want to use during the holidays. So it has quite a big impact on people's well-being in this region. The second picture shows the pictures of coral reefs, and that's a bleached coral reef. This is another example of a regime shift. If temperature goes above 29 degrees something, I think it is, in the water for more permanent time, then the coral reef become bleached, and that could be a permanent change if the temperature increases to long-lasting. If it goes down again, then they can recover, but if it lasts for too long, they will be permanently bleached, and that's very hard to recover from. And this is an example of a forest that is slowly undergoing some dying. I don't know for which reason, but one example of forest regime shift is when you have precipitation decreasing regularly. At some point, there is a threshold where it's not possible to sustain big trees, and then it will die out, and you will end up with a more savanna-like system instead. Fisheries collapse that we heard a bit about yesterday is also another example of these kind of abrupt changes in ecosystems. There are also abrupt changes in Earth dynamics. These changes have not happened yet, thank God, but there are lots of discussions and evidence that they may happen in the past if we don't decrease our pressure on the environment. So these are also examples of potential regime shift to happen that could be studied. So why should we spend time on these issues? Because, I mean, why does it matter? Well, it matters for three reasons. So one is that it has actually big welfare impacts. It can be a big problem if it affects an important resource base. For example, if you have a fish stocks that disappears, it's not nice for the people who are fishing it. They don't get any revenues anymore. It can influence freshwater availability. It can influence the health of agricultural land, so you can't grow food anymore on it and these kind of things. And it's particularly problematic for those people who don't have alternatives. I mean, if we are very lucky in our modern rich countries that, well, if something is not working in the country, we can import it from elsewhere, but not everyone has this chance. So for vulnerable population, this is really a serious problem. The second reason is that because it's likely to become more and more common and the impacts can be high. So even if the risks are small, for example, for these big Earth system tipping points, these are very small risks. But if they happen, the impacts are so huge because we're not going to be able to maintain big civilization on Earth with a climate that is very hot or an ocean that is totally acidified or things like so. So even if there is small risk, the impacts are huge. And also the Anthropocene, this period that this event that we are experiencing now, where people are more and more influencing the way Earth looked like, it also seems to increase the risk of these extreme events. So we have a distribution of these extreme events that become more and more fatal. So we should be careful with this. And the third reason is that because it requires specific management approaches. For three reasons mainly. It's when you have these abrupt changes, your management will be history dependent. So what you have done in the past will influence what you will be able to do in the future. You may not be able to come back to a good regime if you have already destroyed your resource. There is evidence that some type of regulation, for example, price regulation, may not be able to reach an equilibrium efficiently. You may need to have more complex ways of managing the system with two-stage policies and these kind of things. And it's typically not enough to assess marginal change when you want to see what are the impact of this regime. You need to evaluate the whole policy reform to see how it will do on the way. So I want to take a brief moment to just go through, I don't want to go through many definitions, but there are a lot of concepts going around, and I thought it would be nice to just put some of the words out there to see how they relate to each other, at least in my mind. Perhaps not everyone agrees on that, but that's how I see it. So I've studied what we call regime shifts, which are also called in some literature critical transitions. And these are defined as large and persistent abrupt changes in the structure and function of dynamic system. And the dynamic system could be an ecosystem, it could be the climate, it could be a financial system. So these are not only prevailing in natural environment, it could be also in social environment and in what we call social ecological system, which are most of the system that we live in, which are interlinked between nature and society. So what happens when a regime shift occurs is that you have the structure of the dominant feedback that change. What it means is, for example, in this picture, you have two different regimes. You could have a forest or some more like low vegetation regime here. When you are in the forest regime, for example, you have feedback that maintain it, for example. So you have the forest will evaporate a lot of moisture, which provides rain back, which helps it maintain its dynamics. If you end up in a situation when the forest shifts, so it becomes more lower vegetation, you don't have this dynamic anymore. It will become very difficult to regrow the forest because the soil will be covered by grasses, so it's more difficult for seeds of trees to grow, and there will not be enough moisture to help the growth of the trees. So that's the kind of dominant feedbacks that we're talking about. And this change could happen when what we call hysteresis or even irreversibility. So hysteresis is when coming back to the original regime is very difficult. You have to make much more effort than you had to make to flip the system. And irreversibility means it's not even possible to do so. And often in this system, you have slowly changing variables that crosses a threshold, and this is often what triggers the regime shift. That together with perhaps an external shock if the system is quite vulnerable, and you have, for example, coral reefs in Jamaica in, I think it was 1998, they were a bit damaged, and then you had bad weather events that flipped the system to a very nutrient-rich system instead. So triggered a regime shift. But when you look only at non-stochastic events, what happens usually is that you have a slow variable that changes, passes a threshold, and that creates a bifurcation in the system. So you can represent this mathematically. And here is some ways to model threshold that we have found in the literature. So the one I've used the most is this one, the holding type 2, which shows so you have a slow variable that changes and it has barely any impacts until you approach a threshold, and then it starts changing the behavior of the system, and then you pass the threshold and you stabilize on a different level. At the limit, it can become this type of threshold. That's the type of threshold Eric and I, and mainly Eric and others, have studied instead, and that works as well to model this kind of system. Another type of change that has been modeled a lot is the depensation, for example, in fisheries, that it caused by, for example, the lack of, when the population are too small, they don't get to mate, and then it's, you have a collapse of the population. So that's then the threshold would be here when population numbers become lower than, here's an arbitrary number 2, then you have not possibility to regrow. Mathematically, and I will not show many equations, and you will see that most of these equations are actually looking the same, so don't be scared, but here come a few of them. Mathematically, you can model it that way. So this is how to model, for example, a regime shift in pollution. So you have a recipient where you have a flow of nutrients, U, and a discharge of nutrients from the recipient. It could be a lake or something. And by adding this term, we get, for example, a release of nutrient from the bottom sediment. When there is too much load of nutrient in the lake, the bottom sediment might start releasing nutrients instead of absorbing it, and that creates a threshold dynamics. So this function I have used a lot, and I like very much, is used to model this kind of threshold. And it's very nice because the V here shows the maximum level that the variable can take, and the Z here is the value of the threshold. So if you go back in this figure, so you would have the V here is the level here, the maximum level. The X was the value of the threshold here, and the exponential alpha, no, the Z is the value of the threshold. The exponential alpha here is represents the sharpness of the threshold. So I like this function because it can be very general. And in the limit, when the alpha goes to infinity, you get something like this, which is the Nevdal way of modeling threshold, and others have done that as well. But then you have a discontinuous shift, so when So you get a jump in a state variable when that happens. If you have a resource system instead, you can use the same terms, but you instead have a logistic growth in the resource. So that's also a way to model a regime shift that I've used in the paper from 2007, for example. Resource growth with depensation, you can model a bit differently. The circle got moved there, but then you can add this kind of term instead that makes the logistic growth function depensate instead. But in this system, you can have different types of thresholds. So we think in the first place about the ecological system threshold, and these would be, for example, in a lake, the threshold that makes where the lake goes from being clear and to being dirty or eutrophied. But if you optimize over this system, you optimize the management of this system, then you get another kind of thresholds, which is the indifference point, the point where you are indifferent between if you are in a eutrophied lake, wanting to go back to a clear lake, or accepting that, okay, this is okay, I will stay with the eutrophied lake. Because these two thresholds here and there are not necessarily, they could be the same, but they're not necessarily the same. Sometimes it is worth to make efforts to go back to a non-eutrophied lake if you want, if that is what you want. Sometimes it could, this threshold could also be here. So it depends on how the system looks like, but this threshold may not be the same. And a third type of threshold is related to risk. When, if you have uncertainty in this process, when can you, in which condition are you in a situation where there is no risk of a regime shift happening, and when are you in a condition where actually a regime shift could happen? And this is important if you want to have a precautionary approach and want to avoid passing threshold, then you may want to know where this risk threshold is, because that's where below this threshold is when you are safe. And sorry, I forgot to say I have a cold of some sort. My voice is a bit wobbly, so bear with me if I start speaking very strangely. So here is a few of the aspects I want to go through about that are more linked to economics today. And they are inspired from a paper, an overview paper that came from an ASCE meeting many, many years ago. And in that paper, we talked about different aspects, but I want to lift these different issues, the slow variables and feedback, human behavior and strategic interaction and how that influences this, different degrees of connectivities, and policy implication. So first, slow variables and feedback. And that comes from a paper that is very old, but it's one of my most cited papers, so I'm a bit proud of it. So that's about how I used techniques from other disciplines to try to analyze how you could analyze the change of fast and slow dynamics. And it's quite simple in a sense, because what you do is you have a system that looks perhaps like this. You have a series of dynamic equations for some fastly moving variables, and you can represent it like this, and here would be like the more convex standard problem, and you would have an extra term that is here, that is more a threshold term, that would be dependent on a slow variable. And here you would have the equation for the slow variable that is dependent on both of these variables, the change of it. And this epsilon here just represents that this is a slow variable because it's a very small variable. So this change is very, very slow. And to analyze this type of system, you can do like this. So in the limit here, you put epsilon equal to 0, which means that you only look at this equation, assuming that the slow variable is not changing. But then you don't stop there, because you also want to analyze what happens in the slow system. And that's what happens here. So you transform the time scale of the system, and you obtain something like this, where the epsilon moves on the other side on the fast variable. So what you do is that now you analyze the slow variables dynamics, like there were your regular time scale, but you take this equation, this will be very small, so this will be 0, this will be close to 0, and you can just approximate it by this fast variable being in equilibrium. And when you look at these two parts of the system, you get a much more complete picture of what's happening. And here is what type of result you can get, for example, in a coral reef. So here is a phase diagram showing algae and algae and fish dynamics in a system that with a tipping point. And if you have a low fishery, you would have something like this. So you have two possible stable equilibria. This one. This has low algae, high fish. This has high algae, low fish. So you prefer to be in that one. But if you start fishing, you will push the system, this equation, to here. So you see it decreases. And that could be fine if you only look at faster variable. But if you look at the slow variable, you can see that if you start fishing, you're also influencing the coral that will start moving slowly. So you can have a long-term effect where this curve will decrease even more making these two equilibria disappear, and you are left with only the equilibrium with high algae and low fish. So that's how you can analyze it. So here is the slow dynamics analysis, where you see in which part of the system you have one algae-dominated state, two stable states, or one coral-dominated state. So this is for the fast and slow dynamics. We also looked, and that's the paper with Eric that we wrote in 2019 or 20, where we looked at different, how would risk influence this? And in particular, we were very unhappy with the existing type of risk structure that were around, because basically there was only two ways to model risks that we could find in the literature. One was what we call time-distributed catastrophe, and it's a bit like having this dynamite with a long fuse. You don't know the size of the fuse, but you know that when it's lit, it's going to burst. So the probability that you have a regime shift is going to be 1. In any case, it's just about the time of when it happens. And we felt that that's not really how it happens, because in some system, there will not be a shift. And you know that except if you get a meteorite bumping on the Earth and wipes up everything. But that's not the type of problems we're looking at. So another way to model uncertainty was to use state space distributed catastrophe. And the dynamic there is a bit like this woman walking on thin ice. So she can make a step and, oh, it holds, but the moment it doesn't hold, then you know that, well, then you have the regime shift, it has happened, and you can't go back either. So in that case, the probability of the catastrophe is either 0 or 1, depending on whether you manage to avoid the spaces where there is a risk of a regime shift. So what we did instead, we wanted to introduce the effect of these slow variables. So because sometimes you move in space and nothing happens, but if you stay long enough, it's going to happen anyway. So you want to be able to differentiate between the situation when you move and you will flip and you will drop in 3 or 4 or 5 or 10 years, or the situation where you move and you will be safe. So that's so to do that, we introduced another way to model what we called inertia risk, where we introduce a slow variable in the form of stress dynamics that complement the standard hazard rate. So we have a hazard rate that is dependent on the state variable, but also on the stress dynamics, which is a second state variable. And this stress dynamics is a function of its own dynamics and the state variable. So that's how we kind of introduce lags in the risk function itself. And by doing so, we obtain a probability of catastrophe that are somewhere between 0 and 1, depending on how we parameterize the system, which is, I mean, it's a bit more complicated, but it's more realistic. And it can be helpful in some situations to model situations that, for example, we used it with an example in climate change. And what we find is that, one, we find path dependency. So using the wrong model can lead to errors, because once you have passed the threshold, you can't go back. Or even if you can go back, it will be very costly. So it's not the same problem as before. And we also show in the situation with climate change that ignoring this type of risk creates unnecessary risk, and we may cross the threshold even if it's suboptimal. And by being aware of these lags, we can provide enough time to react and avert the catastrophe. And we also show that this hazard rate depends on other parameters than for the other two types of risks, so which also gives indication of what kind of parameters we should start monitoring, right? And some of these parameters is, for example, the slow variables. We don't monitor them. We always work very fast and look at. So there are very few slow variables that we monitor because they don't change. Usually they don't change, so it's not interesting. But the day they start changing, that's when you want to be aware that they haven't changed and they start changing, because something will be happening. So another aspect linked to slow variables is when we looked at, and this is with Maria Arvaniti and Chandra Kiran, who to be fair, they did all the math because this is a very fancy mathematical model. I was able to understand how it worked and check that it was okay when they explained it to me, but I would never been able to do that without them. So that's where you need co-authors, right? So what we do that is, there is what we look at what happens when people are impatient, so when there is a present bias in the objective function. And for being able to do that, we had to take other tools because it was quite difficult. So we modeled the regime shifts as a change in the distribution of the future stock of the resource that we model, rather than a dynamic system shift that we presented before. And we look at both situations when there are lags when we cross the threshold, so we will get a flip later on, or when there are no lags, so when we cross the threshold, the flip happens right away. And the result that we have with this model, I won't go through the equations, you can read the paper if you are interested, but yeah, it's too much to show here. But we show that the extraction increases in the degree of present bias, and it increases in the threshold. So what it means is that no matter, and this is a very general model, we didn't have to specify the utility function or anything very much, so no matter what happens, people will pass the threshold if that's the best thing to do for them, and they will pass it in any case. So that's quite a gloomy result. I didn't like that result at all, but as a scientist, you have to present that in any case, right? But it made me reflect a bit. So how do we do? So one reflection I had after this paper and after other paper, how do we track? And I don't have any answers to that. So that's something we may want to discuss later on. So how do we track slow variables and inertia process? How can we do that in the best way? And which one do we want to track? And are we doomed if present bias prevails? What if everyone is impatient? Does it mean that we will just destroy our planet and be fine with that? Or can we do something about it? And there are empirical evidence that we are actually seem to be acting very impatiently. If you look at, there is a literature called great acceleration literature. You may have seen it with papers with lots of hockey sticks measures showing that the last 50 or 70 years we have actually blown the ceiling of many measures that do, and that's not going to be sustainable. But we also have a very nice result from behavioral experiments showing that people are actually not always behaving that impatient. I mean, it's not always that negative. So, and I will talk about that like now. And another question I have is also, could we put in place policies addressing present bias? Is it something, how would that look like? Perhaps that's something we want to discuss later on. But now I will want to just talk a bit about the human behavior and strategic interaction, which is another aspect of research that I've worked a lot with, thanks to mainly two colleagues of mine, Therese Lindahl and Caroline Schiel. So Therese was a good friend and colleague during the PhD time, and we started working together, and she was very interested in experiments, so we introduced me to that, and then we were very lucky to have Caroline Schiel as a PhD student, and all together we developed a nice framework for how to analyze this tipping point aspect in experiment. But first, I want to go through what are some of the results in this literature. You have typically two types of experiments. You have public good experiments and common pool resource games. And the results vary a bit depending on different factors. So for public good games, you have literature that identifies different factors triggering coordination. And here are some examples. So you can see the higher risk, repeated game, and communication help trigger coordination, and then we will more easily stay away from the threshold. And you have factors hindering coordination. So uncertainty around the critical contribution is one. Heterogeneity is another one. And please, this is not an exhausted list of literature. So if you are not on the list, and I've provided a lot of contribution to that, I'm sorry about that. And then we have this common pool resource games where you have two types of situation. You have factors facilitating the sustainable resource use. It could be communication or punishing free riders, and factors preventing sustainable resource use, and it could be threshold uncertainty. But all this literature looks at static game, and it's not dynamic in any way. And we were not so happy about that because the type of resource that we are looking at are dynamic. So we developed an experimental design to look at dynamic games with thresholds. There were experimental design to look at dynamic games, but they did not look at thresholds. So what we did is we have a very simple thing. We have 3 or 4 people in a room or the field that play a repeated fishing game or resource management game. They can earn money based on what they harvest. And they don't know how they harvest for several rounds, and they don't know how many rounds. And they get an update after each period about how much the resource is left. We allow communication. We don't force them to communicate, but if they want to communicate, they can do that. But their pledge is secret, so they can cheat on each other, which is quite fun to see that they sometimes do. And we have done that in multiple settings, and I show an overview of the different settings that we've been looking at. So both in the lab and in the field. So in the lab, we've mostly tested those different treatments. So this is a baseline treatment. So this represents a resource stock without threshold, where we start at the maximum resource stock here, and this shows for the different level of the resource stock how much the resource will regrowth. And we present people with this figure, and in the threshold treatment, we present them with this figure. So when they harvest the threshold beyond a certain, the resource beyond a certain threshold, the renewal rate of the resource will drop, and then it will be quite hard to regrow the resource because we have some hysteresis, which is symbolized by this region here. We have also experimented with like putting a quota instead of the threshold and to look what happens. And here's an example of the kind of design we've had in the field. And it's been mostly with fishermen in Colombia and Thailand, but we also had a nice experiment designed for elephant and grassland dynamics in Zimbabwe, which is represented here, so where we have 2 resources that interact and threshold represented in the same way. And here is the design for the fishermen, where we have simplified the resource, but we have different regrowth rate below the threshold when we have the threshold. And the nice thing with these experiments is that here I show the findings that we have from the most simple situation in the lab, but in many of the field we find similar situations. So when we have no thresholds, we find the standard result. People overexploit in 60 or 70% of the cases. They overshoot and destroy the resource. When we have threshold, people seem to coordinate, and they talk. They seem to actually start communicating. They see the threat, they talk to each other, they analyze the problem, and they get better at managing the resource, and they very rarely overshoot it. I mean, they still do, but not much. So you can see that on average, they are also much more. This is the threshold. I think it's wrong, actually. It should be, this is the situation where the threshold are more efficient than the one without the threshold. I think we have the wrong scale here. Oh, no, it's all right, sorry. So this is non-threshold, yeah, not threshold, and this is the threshold. They are much more efficient in managing their resources. And even in the field, we find this type of result, but it's very context dependent. So Caroline, and I was not involved, Caroline and Juan Rocha, they did experiments in Colombia in 4 different fields, and then you could see very big differences in how they were able to avert the threshold or not in these experiments. And mainly it was based on whether, it was correlated with whether these fishing fields had, oh, help. I need to hurry. Whether this fishing field had been whether they had experienced threshold in the real fisheries or not. So the question is, how much does context influence the outcome, and in what way? That's something we need to investigate. Could we do experiment to test the impact of present bias on slow variables and group sizes? Because this is always with small groups. We want to see what happens when we have bigger group at the global level. What can we say about that? And all of this. This is just, probably, we got a new paper published 2 days ago, which I really like the title. And this is not a research paper, it's a more perspective paper. So if you're interested in reading about these issues about how behavior and social norms and tipping point can interact, you could read that. I wanted to go through different degrees of connectivities, and I think I will do that, but I will skip the last slides. So here's, and this is work in progress, so it's not been reviewed. But here's how we wanted to, and it's with Juan Rocha, who is a systems ecologist and expert in regime shifts and cascading regime shifts, how they spread across different places. So that's what we wanted to look at. So what happens when you have multiple systems connected? Do these regime shifts spread from one to the other, and how? And we do that by looking at a modeling framework where we link multiple areas where regime shift can occur and we link them to each other. We look both at pollution systems, we call them, so systems where, like lakes, where you can pollute and you have a flow of pollutant and you can flip the system. And we look at resource management systems. And here's so these are complex equations, but they are basically the same as the one I showed you before. The only difference is that, so here you have the pollution system, flow of nutrients, outflow. This is the threshold term. And here you have a resource management, so it's a logistic growth again. And here is the threshold term. And then we just add a dispersion term, which indicates how resources goes from one patch to the other, and how these resources are exchanged between these different patches. And when we do that, and this is just an example from the resource pollution, we see that connecting these with each other actually influences the number of steady state you have in a particular patch. So this is figures showing what happens in a patch when different things flow to other patches where there can be regime shift. And we can have situations where, yeah, that triggers a regime shift, that triggers multiple equilibria, or that triggers a regime shift to a totally different regime. Thank you, Eric. And the same happens when we control the system. So connectivity seems to influence these outcomes. And above all, this is a very interesting framework to test all these things. And now we have put it in the computer, so we're going to run a lot of things and see what happens. And I wanted to go through some diversity aspects, but I will not go through very much to it because I don't have time, but I just want to show you what happened. So that's also a quite old paper, but what it shows is that, and I will pass that, is that diversity plays a big role, and when you have diversity in there, it will also influence how you design your policy, because if you want to do it optimally, it will influence how your policy looks like, and you will have to have it dependent on the role of diversity. So, so that's also an interesting aspect. And a last question that I have not looked much into, but I want to just show what happens is the question, are regime shift motives for precaution? And Art Dessous, who is here in the room, has worked a lot on this. And Eric has also worked on this. And there the question is more and more, it depends. It's not so easy. In some situation, yes, it is motive for precautions. In some other situation, it is not. And we need to study this more, I would say, to see when we should be we be precautious or when should we not? So, and this is my last slide. So what I wanted to say in this presentation is that regime shifts are not just rare events studied with fancy tools. They are becoming pervasive. They are something that we will experience. We are experiencing a big regime shift at large scale, which is climate change at the moment, which is changing, is going to another stability domain as we speak, and we will see its impacts if we're not able to prevent it. So this is something that we need to take into account. And I also hope that I've been able to show you that it influences policy. The way you have to react to this regime shift will be different compared. You can't use the standard model most of the time. In many situations, standard model will still work. But when you're approaching a regime shift, when you have the risk of a tipping point, you risk to make big errors when you use the standard model. So you have to think about that. So I think I also showed you that we need to do a lot of more research in this field to understand concretely what's happening. I mean, a lot has happened. I started with this, I think, more than 20 years ago. A lot has happened since then, but we still have a lot to do. The question is, we can't wait for the research to be done, to act. We need to act now, because if we wait too much, this regime shift will have happened. So we need to find ways to overcome this. And the question is, can we even optimize on this? Because it's so many different parameters that we don't know what's going to happen. If we have forgot something important, our optimization will be wrong. So I'm not sure even that we want to do that. I'm more and more leaning towards precautionary approaches to try to avoid irreversible things that we don't want to go into. But that was to provoke you to ask questions now. So thank you very much and for listening so attentively, and I hope you will have some questions so we can have discussion.
Well, thank you, Anne-Sophie. That was, as I suspected, informative and illuminating. Any questions from the floor?
Don't be silent. I kept you 12 minutes for questions, so you just have to ask them. Yes.
So thank you very much for this very inspiring and multifaceted talk. I have one short question. In these models, you usually assume, or you have the information how the different regimes look like. You have a tipping point and you know what's on the other side. But what do you do when you do not know what's on the other side? You just know there is a catastrophe, and if things happen that haven't been observed elsewhere, what do you do then?
Well, that's a hard question, and I'm not sure I can answer that. But I think in that situation, perhaps go back to granny common sense that Rashid had yesterday. So what happens when you know something is going to happen, but you don't know what? And I don't know, perhaps you want to wait a bit before you cross it, right? Unless you are really a risk-loving person. I think it depends. If it's a small system that you can have alternatives, and then you may want to test. For example, before we knew about this lake system, there were many lakes, and Steve Carpenter made a lot of experiments on lots of lakes in Wisconsin, where there was possibilities to do so. So then he didn't know what would happen when he put some nutrients in the system or started fishing, and he flipped some of these lakes, but it perhaps didn't matter so much because there were many other lakes, so he could study it, and that was nice. But with the planet, would you do that? I don't know. But the thing is also, perhaps you don't need to know what's on the other side to take action. You have a feeling, so are you happy with the state of the art on this part of the thresholds, and perhaps you can just work to maintain that, and that's good enough. You don't need to optimize things, and yeah, perhaps it would be much better on the other side, but if you don't know, it could also be much worse. Then perhaps it's good enough to stay on this side. I don't know if that answers your question.
Okay, then it's art received. You can just give it to
Carine, yeah. Anne-Sophie, thank you very much. It was very nice. You can say these tipping points are a wicked problem, right? Because you showed initially that we can have huge disasters. There's one other wicked problem in the world, that's the lack of cooperation to solve all these issues. And the interesting thing is that, in a way, there's a positive result in the literature, in the experimental literature, especially introduced by Barrett and Dallenberg, where they say if you have a tipping point, you increase the level of cooperation. And you've done a lot of experimental work afterwards, and I was curious if you have done investigated similar things, and if you find similar conclusions, or that actually cooperation increases, which actually is a positive result from analyzing these tipping points.
Yes, I mean, it is, the result of our experiments show that when there is a tipping point in the system, in the experiment, compared to where there is not, people tend to cooperate much better. But it's in an experimental design. It's with 3 or 4 people, and yeah, it's a very controlled design. But what I'm very optimistic about this is that this result seems to be prevailing also among students in different universities, among fishermen in different communities, except some few communities where they had already destroyed their resources. So I think there is hope. But yeah, it's difficult. So the paper I showed you that was published 2 days ago, Titanic Lessons for Spaceship Earth, that's a paper where we investigate. We do not do experiments there, but we investigate in what way we can learn from behavioral behavioral failures that happens on the Titanic to help us better manage Spaceship Earth, and how that can help us improve our international organizations so that we can find ways to and I don't know if we have the answer, but I think we should be. I'm a very optimistic person. It looks grim, but I think when people sit down and talk to each other, they can do miracles, and that's what we need to be able to do. The tricky thing is to scale it up to the big scale, I think. Carina?
First, thank you for a very interesting talk. This is not my field at all, and I really found it intriguing to listen to you. So I have 2 small questions, and mainly to increase my own understanding of what's going on here. So the first one is concerned the slow variables. So you mentioned that, you mentioned only in passing really, that when it comes to climate change, we tend to overlook what is happening with the slow variables. So I was wondering if you could give an example of such a slow variable affecting climate change that we should be studying, but we are really not.
Well, sorry.
Okay, I can wait with the second one.
No, well, I mean, for climate, we know now what variable it is, but we are, I mean, we have been monitoring the carbon dioxide stock in the atmosphere for a long time now. But before it was changing, we didn't. The ozone hole is one of those where we had no clue that it was influencing the atmosphere. I mean, when they saw that there was an ozone hole starting to build up, they thought it was a measurement error. So okay. That's the kind of things that you want to be paying attention to.
Right, I think I understand.
Another aspect that related to climate change would be perhaps the rate of acidification in the oceans, which is tightly linked to carbon dioxide in the atmosphere. So how to monitor that. But in other, I mean, climate change is one big thing that can flip. There are many others. And I think what And I'm like you, I don't know, we don't know exactly which are these variables we should monitor. So perhaps that's something we should sit down and think through. So what could be good candidates for these slow variables that could be starting moving? And one way to do that is to, I think, look at complex system dynamics, try to put the map, not trying to model everything in detail, but try to put a map of what is influencing what, in what way. And that usually gives good ideas, because then you can identify very far away sources of changes that you didn't think about, and see and follow them through the system and see what that could trigger a flip there if that happens. And it's blue sky research in a sense, because you are really searching for scenarios of things that haven't happened in the past, so it's a bit hard. But there is a science for that as well.
Right, thank you. So the other question was concerned the present bias test. Mm-hmm. So you told us about this paper where the result is that if we are actually present biased, we are doomed.
Yes.
So can you explain a little bit more about the intuition of that result? And doesn't it matter how present biased we are at all? Is it enough that we are present bias?
Yeah, that's the tricky part, in that it was quite it was quite enough that we had this this bias, present bias discount rate in the model was enough to give that result, which is very depressing for me, because somehow we all have some sort of present bias in our gene. But so I think it is also intuitive. I mean, we know what we have now. We don't know what we will have in the future. So it gives an incentive to consume more now. But I'm also thinking that perhaps if we give people some hope, they will want to work more. I don't know. I'm ideally, I don't know exactly how, but it makes sense, right? It makes sense. But I'm not sure I like this result, because I would want to have hope for my future generations. And I think it may have to do perhaps with us not taking into account the future generation. We don't do that in the paper. Perhaps that would change the result. But the result was very general, but builds on the assumptions we have in the model about how to model present bias and not having other generations and these kind of things. So I don't know.
Okay, thank you very much. Then that's Thomas Sterner over there has a question. But keep it brief, please.
Thank you, Anne-Sophie. That was a wonderful speech. I like particularly the way you sort of test and discuss the usefulness of modeling approaches. And I was wondering, you didn't talk very much about social tipping points or tipping points in our own behavior. And we see the rise of authoritarianism, and you have the feeling that this accumulates and that there are, in fact, points of no return there as well. And also in the way we manage. It seems people get upset about the instruments to solve environmental problems, and then they go the opposite direction and choose to eliminate those instruments. So, do you think it's promising to use this approach also for human behavior and social systems?
So the reason I didn't mention those things is that I haven't studied them myself very much, but there is a lot of research on social tipping points, and there is a lot of research of tipping points in social ecological systems, so interacting systems of nature and society. And I would say that, so some people would say, oh, it's different dynamics, that social and ecological dynamics are totally different. And there are differences. So in the social system, the people who are taking action are also consciously taking action, are also part of the system. So it makes it a bit different, but I still think that you can still model this system as a set of dynamic equations with thresholds here and there and slow variable. I'm pretty sure that works, and that's also how they are often analyzed. And in the same way as in ecological system, when you have social tipping point. You can have social tipping point to a worse state or to a better state. And there is a lot of literature on transformation, which is some sort of trying to trigger the social tipping point towards a better world. So there is, yeah, I think the short answer would be yes, I think you can apply this system. The longer answer is you need to be careful because the social and the ecological don't really work in the same way. But if you invite people who know these different types of models, you will be fine, I think, and you may discover new things.
Thank you very much. And thank you for a great presentation. And well, see you again next year. And I'll...
Thank you.